I'm going to do something which you might think impossible, namely to present some EEG data which decide between the possibility that defeasible reasoning is logical or probabilistic. And you're not going to believe this. So I hope for a ferocious discussion. All right. Logicians, when they huddle together in their institutes, feel quite powerful. But when they venture out in the wide world, they are soon confronted with pieces of prose like this. Much of our reasoning with conditionals is uncertain and may be overturned by future information, that is, they are non-monotonic. But logic-based approaches to inference are typically monotonic. Yeah, so this is from a book by Oxford and Chater, which in parts betrays a considerable ignorance of logic. Moreover, to the extent that formal logical approaches embrace non-monotonicity, they appear to be unable to cope with the fact that it's the content of rules rather than their logical form, which appears to determine the inferences that people draw. So there's the opposition between form and content that is customary in the psychology of reasoning literature since the work of Johnson Laird. And now let's go to the last sentence. Probability is the calculus of uncertainty. Yeah, so they argue that probability is better equipped to deal with content than logic. And the argument for this is that probability is the calculus of uncertainty. Now this suggests that there is only one form of uncertainty. And this is something we'll question. And we'll question this using the following task. This is the so-called suppression effect. So you start out with an ordinary modus ponens inference. If Marion has an essay she studies late in the library as a conditional premise, and Marion has an essay as a categorical premise. And then about 90% of subjects answers yes to the question, does Marion study late in the library? So you may wonder what the other 10% are doing, but there's a good story to tell here. Now, if you add another conditional premise, if the library is open, Marion studies late in the library, then, and you again ask the question, does Marion study late in the library, then that percentage drops. The numbers vary, but a typical number is a drop from 90% to 60%. Yeah? And one says, in this case, that the inference modus ponens is suppressed. At least that is Byrne's expression. It may not be entirely felicitous. Yeah, so this goes against the monotonicity property of classical logic. This experiment was designed to be a crucial experiment in the debate between so-called mental logics and mental models. The idea being that if modus ponens is a surefire rule, then you apply it no matter what. Yeah, and so you should also apply it in the presence of another conditional premise like this. And the result was taken to be the death blow to the mental logic school. Well, when a logician sees this, he or she says, what's happening here is that subjects employ some kind of non-monotonic logic. Yeah, it doesn't go against any kind of logical reasoning, it's just not monotonic logic. But this phenomenon has given a boost to probabilistic analyses because some, especially Bayesians, claim that logic is unable to handle this phenomenon. So what we are going to do today is first raise your blood pressure by asking the question, is Bayesianism indeed equipped, or perhaps better equipped, to deal with this form of non-monotonicity than logical mechanisms? I will present two formal models, one more or less Bayesian, one of a logical kind. And then I use some data from a recent EEG experiment, which seems to decide between the two formal models. And then I want to throw up some issues for discussion, namely about rationality principles for what I call realistic Bayesianism. So what is unrealistic Bayesianism? That's Bayesianism that assumes that you have a prior probability defined over all events. Yeah, so if you don't make this assumption, which I think you are forced to do for cognitive reasons, the question is what rationality principles remain. Right, so here's our first logical model. That is formulated in a non-monotonic logic called logic programming, which was not designed to be a non-monotonic logic, as the name implies. It was designed to be a programming language. But several people independently observed that the way the semantics of this programming language works makes it ideally suited to be defeasible logic. Okay, so what is logic programming? It consists, first of all, in a considerable restriction in the syntax of the logical language. Yeah, so logic programs, to a first approximation, consist of horn clauses, which are of the form a conjunction of atomic formulas, an implication, and as a consequent, an atomic formula. And that restriction in the syntax allows for a very different semantics from the classical semantics. So what is the semantics? Let me give a simple illustration. Suppose we have one such clause, as it is called, and there are no other clauses which have the same consequent Q. Then we say, if all the PI are true, so is Q. That's just modus ponens. Nothing spectacular so far. But if some PI is false, then we say, so is Q. And that's called the closed world assumption. And you see that the classical fallacy denial of the antecedent is built in here. Yeah? Or in other words, you replace the implication by a by implication here. Yeah, that's the same thing. Yeah, classically you couldn't do this, but in this context you can do this. So you can think of this causally. If Q is an effect and the PI are jointly sufficient to produce Q and individually necessary, then you say if this jointly sufficient set of causes does not occur, then the effect can also not occur. Yeah? Right. So that is called the closed world assumption. If there are several clauses, and now I see I made a typo, forget this by implication, this is a simple implication. it goes only this direction. If there are several clauses, then you first take the disjunction of the clauses, of the antecedents of the clauses, and then you replace the implication by the by implication. So this says, if you have several clauses with Q as a consequent, then Q is false if every one of the antecedents is false. Yeah, so that's again denial of the antecedent. Okay, there is a story to tell about negation, but I'll do this as I go along. So how do you analyze the suppression task in this framework? Well, you assume that, say, the deep structure of the conditional is not something of the form A implies B, but there's always a hedge there. So you say the deep structure is A and nothing abnormal is the case implies E. Yeah? So the nothing abnormal is the case is the hedge. It's always possible that there is some disabling condition, as one says. Yeah, conditional is never absolutely true, and that you can easily verify when you think of conditionals in ordinary life. Okay, now we apply this closed world assumption to the abnormality. So what does that mean? We first look at the case of modus ponens with two premises. If Marion has an essay, then she studies late in the library, and the categorical premise, Mary has an essay. That means we know this, and we know this, but we know nothing else. Yeah? Then the closed world assumption says there's no reason to assume that there is any abnormality. There's no reason to assume the existence of some disabling condition. And therefore we can conclude that nothing abnormal is the case, which means that we can cross out this conjunct, and we get A implies E together with A, and you get E as in the ordinary modus ponens. Yeah? And so what happens with the 10% of subjects who refuse to draw the inference modus ponens? Yeah? Well, if you interview them, you see that they consider some possible disabling condition. Yeah? They make this hidden representation explicit. Okay, now suppose we move to the three premise case. Yeah, so we have an additional conditional premise: if the library is closed, if the library is open, Marion studies late in the library. That means that the possible abnormality, the library is closed or not open, comes to light, and that we express the fact that it is an abnormality in this way. The library is not open implies that there is an abnormality, but there is no other abnormality mentioned in this three-sentence discourse, which means that we can replace this implication by a by-implication, and the conditional becomes A and C implies E. Or in words, if Marion has an essay and the library is open, then she studies late in the library. Yeah? But given A only, you can no longer infer E. So that's the logical explanation of the suppression effect. Right. Now, this analysis does some work. So for reasons which are too complicated to express here, we, meaning Keys and I, made a prediction that subjects who suffer from autism would suppress considerably less in this task than normal control subjects. And that turned out indeed to be the case. Yeah? So the analysis has some cognitive merit. Okay, now we move to the second model, Bayesian probability. So what is Bayesian probability? The axioms of probability plus a rule of inference, Bayesian conditionalization. We would take the simple form here, not the Jeffreys conditionalization. If E summarizes all our evidence and E occurs, then for any S, the A posteriori or final probability of S equals the A priori or initial probability of S conditional on E. Yeah? So this is probabilistic modus ponens. And furthermore, we assume the standard Bayesian assumption that there is a probability defined over all events of interest. This is by no means an innocuous assumption. It puts considerable demands on cognitive storage. Yeah. The reason being that probability is not truth functional. Yeah, so in classical logic doesn't put much demands on storage because you can compute the truth value of formulas via truth functionality, but you don't have this for probabilities. Okay, so here's the point I want to throw up for discussion, to which I don't have an answer. So in practice, the sets of variables of interest grows. Yeah, the algebras over which the probabilities are defined grow. And what are the reasonable inference principles when you have this situation? So how do you transfer the probability from one set of events to an expansion of that set? And we'll see that this lies behind the suppression task. Okay, now why Bayesians think that Bayesianism is very suitable to analyze non-monotonicity effects like the suppression task is that you have in probability, of course, inequalities of this form. If you add something to the condition of a conditional probability, then you have in general this inequality. But there is a problematic form of non-monotonicity, that is that the initial conditional probability may be different from the final conditional probability. And this, we'll see, is fraught with difficulties. Okay, so what is the analysis that Oxford and Chater, as to name two prominent examples of Bayesians, what is the analysis that Oxford and Chater give? So the subjects are given the modus ponens argument, and when processing the first conditional, if Marion has an essay she studies late in the library, the subject interprets the conditional as a conditional probability first, and second, the prior conditional probability is more or less equal to 1. Yeah, so this is the event she studies later in the library, this is the event Marion has an essay. Yeah? And then when A occurs, by Bayesian conditionalization, you have that the posterior probability of E equals 1. Yeah? And that gives you the modus ponens inference in the probabilistic form. Okay, so now they want to argue that when you have the second conditional, if the library is open, Marion studies late in the library, should lead to a considerable decrease in the final probability, or the a posteriori conditional probability. Yeah? And how do we get this? Is there a Bayesian explanation for this transition? Okay, let's try. Let's do a decomposition. So the initial probability of E given A is this expression, where C stands for the library being closed. So it's the standard decomposition, where you have to have terms, the probability of the library being closed conditional on Marion having an essay. Well, we can simplify this expression because these events are independent, so we end up with an expression of this form. Well, what do we want to get out of this analysis? We want to get that the final probability, final conditional probability of E given A is much smaller than the initial conditional probability of E given A. And that is so if the final probability of C is much larger than the initial probability of C. Yeah? Because this term must be made small in order to keep this term. But that is very strange. Yeah, so initially the C must be small, the probability that the library is closed must be small, and when the possibility that the library is closed is highlighted by the second conditional premise, then that probability suddenly increases. Yeah, it's not that you have no evidence of any sort about a library, it's just that this event has become salient. Yeah? Before that, it was perhaps not even in your mental algebra of events, but suddenly it is an element of your algebra. And in any case, its probability increases due to its becoming salient. So the second question to address in the discussion is this a Bayesian procedure, or is something else going on? Right. I said just now that this event that the library is closed may not have been an element of your algebra, realistically speaking. Yeah? But Bayesians assume that there is an algebra of all interesting events and a probability distribution defined over that entire algebra, because you need this for the validity of Bayesian conditionalization. Yeah, so you can easily check that if, for instance, if you have multiple algebras, then Bayesian conditionalization is, in its original form, is no longer valid. So it must be replaced by something else. Now there is one formalism for doing probability with many algebras and algebras that grow over time. That's Renyi's axiomatization. That's different from Kolmogorow's formalization. where you have a single algebra and a single probability measure. But here you have families of algebras and families of probability measures. However, one of the axioms that Renyi proposes is such as to destroy the possibility of real novelty. Yeah, so you couldn't reproduce the argument that I sketched just now for the suppression task in Renyi's axiomatization. So the question that I now want to address is whether these difficulties, these theoretical difficulties for Bayesianism, actually imply that it is impossible for people to reason in a Bayesian way. And at the start of this discussion of an experiment, I want to say that I take Bayesianism very seriously, yeah? Meaning that for the purpose of this talk, we take it to be a computational model of the phenomena, which should somehow be implementable in the brain. So if subjects reason according to a Bayesian model, that should somehow become evident in behavioral and neuroimaging predictions. It's not just an as-if story. So what we'll do is compare EEG signatures, so particular signals, of Bayesian reasoning and closed-world reasoning in a watered-down version of the suppression task, where we have eliminated the problem of its novelty. And there we'll see that even in that case, Bayesianism faces an uphill task. And that's from a paper in the Journal of Cognitive Neuroscience in 2010, which was written for an entirely different purpose. It was a control study for an EEG study of reasoning with exceptions in autists. But I later noticed that it said something about probabilistic reasoning. So here we have the vanilla version of the suppression task. So what is vanilla about this? It is easier in the following sense that the disabling context is given at the start. So here's an example. This is the first sentence of the discourse. Liza probably lost a contact lens. If Liza is going to play hockey, then she will wear contact lenses. Liza is going to play hockey, yeah, and the conclusion is, or is not, Liza will wear contact lenses. Yeah, so it's easier than the other version of the suppression task, where the disabling condition was hidden in the conditional. Yeah, so here it is stated as a fact. And I must confess that for that reason, I tried to dissuade the main experimenter, Judith Pijnacker, from doing this task, because I said this is not going to work. I was totally wrong. Yeah, the results are even more striking. So in the congruent condition, meaning the condition where the context is neutral, Liza has recently bought contact lenses, about 90% of subjects endorses modus ponens. Yeah, but by now you know what those 10% are doing. And in the disabling condition, only 45%. Yeah, so the drop is even more significant than in the case of the conditional premise. Well, why is this a good example to study the relation or the processing aspects of Bayesianism? Unlike the ordinary suppression task, the disabling event is given immediately. Yeah, so it is introduced in the cognitive algebra immediately, and you don't have problems with extending the algebra. So the novelty problem is eliminated. Okay, so what is the Bayesian model? Well, we have a disabling event, E. Liza has lost a contact lens that forms part of the initial sample space, and the probability is high, so it is said that Liza has probably lost a contact lens. And again, we follow the tenets of Bayesianism and claim that the meaning of a conditional is a conditional probability. And we do the usual decomposition formula, and we get that the initial probability that she wears contact lenses given that she plays hockey is given by this expression. Yeah? So there is some computation going on. So when the second premise appears, some computation is going on. And if you take seriously the Bayesian view that the meaning of the conditional is given by a conditional probability, then that meaning must be computed while the conditional is processed. Yeah? Okay, so the final probability of the conclusion, the rate of endorsement, say, of the conclusion, is obtained by Bayesian conditionalization, which is itself not computationally intensive. And the idea is here that the percentage of yes answers, so here 45%, somehow reflects the final probability of this conclusion. Yeah, so overall, when you look at all the materials, and I'll say something about the actual numbers later, in 45% of the cases a yes answer was given. And that should be a reflection of this final probability. Okay, now the congruent condition. Liza has recently bought contact lenses. This should have no effect on the probabilistic analysis, right? The context is neutral, so the conditional probability should not be affected by the occurrence of this B. And because this B is given at the outset, you can assume that this probability is 1, and it is in the algebra. And again, the conclusion is obtained by Bayesian conditionalization. But the computation in the neutral case is easier than in the disabling case. So it would seem that if you flesh these sentences one by one, yeah, so first a congruent or a disabling condition, then the conditional premise, then the categorical premise, then if the Bayesian analysis is correct, then you should see some considerable brain activity when the conditional premise is processed. Okay, let's now go for the closed world analysis. So the congruent or disabling condition is represented by a proposition, and the conditional premise, in accordance with our previous analysis, is represented by something of the form P and nothing abnormal is the case implies Q. Now, how do you represent that the condition is disabling? Or even better, possibly disabling? So R represents an abnormality if nothing abnormal is the case. So you can stack these abnormalities. And the reason for doing so is that some people find a reason why the abnormality is not an abnormality after all. And in the case of a congruent condition, there is no link between R and the abnormality. So in the case of the 45% who do not suppress and who do not represent the R as effectively disabling, there is an abnormality here which has as a consequence that the link between R and this abnormality is broken. Okay, so what is the reasoning that the subject does? And now there's an important distinction between the Bayesian analysis and the logical analysis. The closed world assumption is an inference principle, and the Bayesian analysis is a semantic principle. Yeah? The semantics of the conditional is a conditional probability. And the closed world assumption is an inference principle which says, after all the evidence is in, we close the world. Yeah, so what does that look like? So in the effectively disabling case, we have that R indeed represents an abnormality. Whence you have P and not R implies Q, and because you have only P, the conclusion Q cannot be drawn. The other possibility is that the subject considers the R not disabling, so the abnormality dash holds. Whence you can conclude by closed world reasoning that the abnormality for this conditional is not operative. And we conclude that Q follows. And you expect some competition between these possibilities. Okay, so that's the case of the disabling condition. And in the congruent case, there's no link between R and the abnormality, so that you get by closed world reasoning that the abnormality does not hold. Once you get the simplified representation, P implies Q, and Q follows. Yeah? So the closed world assumption is applied at the end, and Bayesian reasoning is applied also in the middle of the argument. Okay. Now what do you see? Okay, so we had an experiment in which we had 80 reasoning problems. All of the modus ponens type, with 40 disabling conditions and 40 congruent conditions, and 80 so-called fillers. And the fillers were necessary so that the subjects did not get in autopilot mode. Yeah, so that they had to wait until the last of the conclusion to see what kind of inference they had to do. So that's important. Okay. One of the interesting behavioral responses is that reaction times in the disabling conditions were significantly longer than in the congruent condition. The closed world model explains this because the computation is much more intensive. The Bayesian model could explain this because we see that we have seen that in the second step, the computation of the conditional probability, the disabling context led to a much more involved computation than the neutral context. But now, let's see what the EEG tell us. Yeah, so we put 28 electrodes on the scalp, which is a relatively small number. It's not as fine-grained as it can be. And in such an experiment, the premises are fleshed word for word. Yeah, so each word takes around 300 milliseconds. And you give, sometimes you show a star in order to indicate that the subject can blink. Yeah, so that you control for this as well. And you measure the brain signal starting at the onset of the last word of the first premise, the second premise. The first premise was the conditional premise, the second premise was the categorical premise, and then the conclusion. And you average over reasoning problems in a particular condition, disabling or congruent, and participants. Okay, so what you see, let me go to the picture. So here are signals from 3 different scalp sites. The frontal central electrode, the medium central electrode, and the posterior central electrode. Yeah, so three sites here. And at 0, the critical word starts. So here of the first premise. This is the start of the critical word of the second premise, the categorical premise, and here's the start of the critical word of the conclusion. Now, what you see, so this lightly colored line represents the disabling condition, and this represents the congruent condition. And you should know that negative is up. So there is a so-called negative shift here, sustained negative shift. Sustained because it lasts for a rather long time. And then this is the only case where there is such a significant shift after the conclusion. Yeah? This looks like a difference, but it is not significant. So we go back to the result. So there's no significant difference between the congruent and the disabling conditions after the conditional premise and after the categorical premise. And you have so-called sustained negativity of the disabling condition in C, in the conclusion. Now it's interesting that this very same signal has been observed in situations where you have ambiguous anaphoric reference. Yeah, so you have a referent, a he, that can refer to 2 persons in the preceding discourse. Now that makes one think that there is some competition, that the signal is due to the competition that we highlighted. Right, but what does this tell us about Bayesianism? The prediction said that we should see either a difference between the congruent and the disabling condition at the second premise, at the conditional premise, or perhaps no differences at all, because the computations were the same. In no way did the Bayesian model predict that you would get a signal after the conclusion. Yeah? Now we want to take Bayesianism seriously as a computational model with a possible neural implementation. And indeed there exist neural networks which are capable of computing conditional probabilities over large data sets, but then so is the situation for closed world reasoning. There you also have neural networks executing the computation. So that there is no difference in that domain. So the question I want to throw up for discussion, for those of you who are better versed in Bayesianism than I am, is there a possible mechanism that can explain why you should see this signal at the end of the conclusion instead of after the conditional premise? Yeah, so the closed world analysis has a clear answer to this. You close the world only at the end when you know what to do, what inference task you have. And again, I must emphasize that that is what the fillers were for. Yeah, so you were never certain what to do, and therefore you could close the world only at the end of the conclusion. So that's the first question I want to raise. Is there a way Bayesian reasoning is implemented in such a way that all effortful computation occurs at the last step? And then the other issue is perhaps Bayesianism, the Bayesian analysis is a detour for something much simpler. Yeah, so we said that you have to assume that an event increases in probability when it becomes more salient. Yeah, so when the possibility for the library being closed became salient, its probability increased. Now perhaps you shouldn't express salience in terms of probability, but follow another analysis by Cummins in 1995, who said that the degree of endorsement of a modus ponens inference depends upon the number of disabling conditions that you can retrieve from semantic memory. Yeah, and in this case, the numbers do not come from the probabilities, but they come from the ease with which you can retrieve particular disabling conditions from storage. Right, so this concludes the talk, and I would be very pleased if someone could come up with a model which explains these data.